Okay, thank you so much for coming, everyone. We can get started. So, yeah, I'm honored to introduce Professor Alex Tartakovsky. He's a professor in the Department of Civil and Environmental Engineering at University of Illinois, Urbana-Champaign, and lab fellow at Pacific Northwest National Laboratory. His research focuses on scientific machine learning, multi-scale mathematics, uncertainty quantification, and Lagrangian particle methods. He received master's degree in applied mathematics from Kazan State University in Russia and PhD in hydrology from the University of Arizona. Thank you.
Thank you for the introduction. It's a great honor to be here. So today I would like to talk about algorithms and theory for digital twins. I would like to acknowledge my collaborators, my PhD students. So what I'm going to present today is mostly based on their work, Yanjie Wang and Mifei Zong. And I also want to acknowledge my longtime collaborator from PNNL, David Barajas-Solana. So digital twins. So it means different things for different people, right? There are many different definitions. I guess they depend on the application of the digital twins. So let me start with our definition of a digital twin. So we define digital twin as a model that allows for near real-time simulations and control of the physical twin under changing conditions. Okay? And also it should allow for the two-way flow of information between the digital twin and its physical twin. Okay, so what we are focusing on are, real-time simulations. So we want to enable very fast simulations of the physical twin and also changing conditions. So we want our simulator, our digital twin, to be able to adapt to changing conditions. So for this, we want to use transfer learning. So we want to make it explainable. And then to enable the two-way flow of information and also to quantify uncertainty in the digital twin. We are interested in Bayesian data assimilation. And so we propose some fast approximate methods to sample Bayesian posteriors. Okay, so and these fast operator learning models that we use for fast predictions of the system, transfer learning and Bayesian data assimilation, we consider this as a foundation of the digital twin. Okay, so let's define the problem mathematically. So we assume that our physical twin can be described by this system by this partial differential equation. So here L is a known differential operator acting on H, which is the state of the system or state variable. So Y here we assume is some property of the system. It's a function of X, so we assume our system is heterogeneous. So F is a source term, can be function of space and time. And then H0 is the initial condition, and then we have a general boundary condition defined by this boundary function G. Okay. So, and then we define an operator learning model as a model that provides near real-time estimate of H as a function of X and T, and as a function of Y, F, G, and H0. And because digital twins are often used for control, so we call Y, F, G, and H0 control variables. Okay. So now you might also know about reduced order models. So these models are designed to estimate H for the fixed values of the control variables much faster than standard numerical methods, right? And there are different types of reduced order models. So which one do we want to use for a digital twin? So reduced order models, they must be re-evaluated or recomputed, retrained every time the control variables change. So in this sense, they are not very adaptable to changing conditions. On the other hand, in general, reduced order models are more accurate than surrogate operator learning models. At the end, these models are just large regression models. So there is a trade-off. So on the other hand, operation learning models, or these surrogate models, they are differentiable with respect to control variables, and differentiable in the sense that the derivatives with respect to the control variables can be computed analytically or using automatic differentiation, and ROM models are not. So because of this, operator learning models, they are more efficient for optimization, design, and control of the physical twin. So for this reason, in the digital twin, we use this type of operator learning models rather than reduced order models. However, we can use reduced order models to retrain the digital twin when conditions significantly change. Okay, so a few words about our general approach. So what we do, we want to cast the digital twinning and operator learning in the context of stochastic partial differential equations. So how do we do this? Well, we represent the control variables, which are parameters in the PDE equation, as stochastic processes with specified distributions. So essentially, we want the digital twin to provide predictions for some specified distributions of the control variables. So of course, this makes the governing equation stochastic, right? So then we generate a labeled data set for training the digital twin using the Monte Carlo sampling of our stochastic PDE solution. Then we use Karhunen law of representation of the stochastic processes to construct what we will show, an operator learning model that can be trainable by parts. As the next step, we use the moment equation approach for stochastic PDEs to analyze transfer learning and design explainable transfer learning algorithms. And finally, we are going to use Bayesian methods to quantify uncertainty in the PDE solutions, which will provide uncertainty in the digital twin, but also use Bayesian methods for data assimilation. Okay, so my presentation will consist of 3 parts. In the first part, I'm going to describe this trainable by part operator learning model. In the second part, I'm going to talk about the analysis of transfer learning. And in the third part, I'm going to talk about approximate Bayesian methods. Okay. So let's start with the operator learning models. So what is the motivation? So there are many operator learning models that learn the solution of a PDE as a function of coordinates and control variables. So this is an incomplete list. So DeepNet, Fourier neural operators, graph neural operators, PCNet. So if you are familiar with the PCNet method, so what I'm going to present is quite similar to this approach. So all these methods, they require a labeled data set, which we denote as D, training. So it consists of the samples of the control variables and the corresponding PDE solution. So n train is the number of the samples. So and once we have this labeled data set, all these models can be trained by solving this minimization problem, right? So, and by the way, if you have questions about the notations, please interrupt me during my talk. So what are the challenges with this? So the number one challenge is, well, I guess these models in general are hard to train for real world applications, right? So why? Well, because for the real world applications, the size of each sample can be very large, right? So let's assume that these samples are generated with a numerical model with, I don't know, millions of nodes. Then the size of each of these vectors will be, equal to the number of the nodes or elements in the numerical model. And then, of course, the size of this guy, H, will be the number of nodes times the number of time steps, which can be hundreds of millions. So loading each sample in the computer memory can be an issue for training the surrogate model. So another problem is that the bigger is our model, the usually fewer samples we have to train our digital twin, because it takes more time to generate each sample, right? So, and because, n train is usually going to be relatively small, we face a potential overfitting problem, okay? So what we want to do, we want to design a model that can be trained using just parts of this data set, not the entire data set. And then somehow we want to reduce the number of the trainable parameters in our model to address these issues. So another problem with these models that they are highly nonlinear functions of parameters, and theta is the parameter of the surrogate of this operator learning model. So most of these models are nonlinear functions of the parameters. So to analyze this model, analyzing these models is very difficult, and analyzing the transfer learning is also very difficult because of the non-linearity. Okay, so we want to design a model that is linear, at least with some of the parameters that we might have to transfer when conditions change. Okay. So now let's talk about the construction of our operator learning model. As I mentioned before, we treat all these variables in our PDE as stochastic processes. This makes our PDE stochastic. So then we can use Karhunen law of expansion to represent all these stochastic processes. So if you are not familiar with scale expansion, this is an example for representing H, the state variable. So we can represent H as its ensemble mean plus the product of eigenvalues, eigenfunctions, and random variables, right? So these are eigenvalues and eigenfunctions of the covariance of H, okay? So we are going to denote this part as a KL operator. So this KL operator again acts on the mean value of the variable, on these scaled eigenfunctions scaled by the square root of the eigenvalue. And again, these are our random variables, and omega is a coordinate in the outcome space, okay? So similarly, we can represent the control variables with KL operators, right? And now size with tilde is a random variable, and subscript, denotes that, for example, f, this is a random variable in the representation of the f stochastic process, okay? So now having all these scale expansions, we can now define the operator learning model as a map between any realization of the control variable that corresponds to this instance omega prime of omega and the instance of the state variable H. Okay, so we have a map from the control variables to the system state. So now alternatively, we can define our operator learning model as a map from the instances of random variables in our control variables and the instance of the random variable in the expansion of the system state, right? And it's what we want to do. So we want to find a map from Xi to it again. So now Xi tilde is a random variable. Xi without tilde is an instance or realization of this random variable. So this is a deterministic vector of parameters in the expansion. So now Xi's become a parameter in all of the expansions of the control variables, and eta is a deterministic parameter in the expansion of the state of the system. Yes.
But a priori, how do you know the KL expansion of the state? Like, how do you know the eigenfunctions to define the eta?
It's an excellent question. So we still assume that we have our training data set. So we just compute it as a sample statistics. Okay. So now, in general, the map from Xi to Eta is going to be nonlinear. So we want to use a deep neural network model, a fully connected deep neural network model to learn this map. Okay. So finally, with this map, we can formulate our what we call KLDNN operator learning model in this form. So it's KL operator acting on the mean value of H given our known eigenfunctions and given this map from the control variables. So now how to train this KLDNN model? Well, we can use the same type of the loss function as we use for all other operator learning models. So however, the issue with this is that, we have this norm essentially of a function that is defined in this way. So of course, to compute this norm, we would discretize the integrals and then use, our training data set to compute it. So however, it's expensive to compute this norm this way. But what we can do, we can use the orthogonal properties of the eigenfunctions to reduce, this term, to reduce this norm, functional norm to the norm just of a vector. Right, and here, so this is the weighted norm of a vector, which is the difference between our neural network prediction as a function of Xi and the reference value of Eta from our, well, I will talk about the training data set that we need to evaluate this loss function. But anyway, so this is a weighted norm, and so this is the diagonal matrix with the diagonal elements given by the eigenvalues of the H covariance. Okay? So now to evaluate this term, we need to know values of Xi I and Eta I, so we can find these values from our full training data set using what we call inverse KL operator, which is given here. Okay. So in essentially what we do here, how we compute, for example, etas, we feed, how we compute this etas, we feed KL expansion of H to each of the sample from the full training data set, and it gives us the values of the corresponding coefficients. And then we can compute parameters in the KL expansions by applying similar inverse KL operator to each of the control variables in the full data set. Okay. So now again, the advantage here is that number one, this loss function is much faster to evaluate than this loss function, number one, and number two, we have to use much smaller training data set. Right, so you can think about it as Xi and Eta as the latent spaces of our control and state variables. So now, what are the advantages of this model? Well, the main advantage is that it can be trained by parts. So now, what do I mean to be trainable by parts? So for example, this is a DeepONet architecture, if you are familiar with this approach. So DeepONet consists of a trunk, and it has X and T as inputs, and then it consists of the branch second branch network. So for our approach, this branch will have many sub-branches. We will have to have one sub-branch for each control variables. And then these sub-branches, the outputs is connected to the kind of main branch neural network. And so now all these neural networks must be trained jointly using our large full data set. Okay? So in our approach, so we can compute eigenfunctions of H, which is equivalent to the output of the trunk, independently by solving eigenvalue problem for the covariance of H. So this is a pre-processing step. And then we can actually split this big branch neural network in parts. We can isolate this part, which is here. And then we need a training data set to train this neural network. And again, we obtain it by applying inverse scale operators to our full data set. Again, this all can be done as a pre-processing step. Parameters for each sub-branch can be computed independently. So we can, construct our KL expansions independently. We can compute our inverse KL operators independently to construct the reduced data set. And then what we can separately train our final neural network. Okay? So all parts of our KLDNN model can be computed separately, which reduces training time and also the memory requirements. Okay? And then, of course, in both models, the final answer is given as the scalar product of the outputs of the branch and trunk neural networks. Okay. Okay, so again, the advantages, all parts can be trained independently. There's no need to access the entire data set, and the DNN, the most difficult part in training, can be done using the reduced data set. So now, of course, the question is how this model compares with other operator learning models. So this is an example. So we consider this synthetic aquifer known as Freiberg aquifer by the name of Freiberg, from a professor at Stanford who came up with this problem many years ago. So there is a river running through the aquifer. There are some pumping wells. So also this aquifer is unconfined. So the equations describing flow in this aquifer is nonlinear. There are some impermeable inclusions. So this is one of the realizations of the conductivity. So it's a log conductivity. So variation in the conductivity and the property of the system is more than 4 orders of magnitude. So this is the typical hydraulic head, which is the state of the system. And so here you can see the errors in 3 operator learning models, FNO, DeepNet, and this is KLDNN. So the scale in each of these plots, the color scale is slightly different. So the DeepNet has by far the largest error. So FNO and KLDNN, they have comparable errors. So the L2 errors are in the table. So deep on it, again, it has one order of magnitude larger errors than in these two models. So we can say that KLDNN has a similar accuracy when, well, in this case, it's slightly more accurate, but we really tried to make it more accurate. But the most important difference is in the computational time. Yes, so KLDNN is 32 times faster than FNO to train and almost 40 times faster than deep on it. Yes.
Is the size of the networks very different between the three?
Well, the size of these parts is the same, but then I don't remember how big these sub-branches and trunk neural networks they used. So in general, of course, for the fair comparison, we want to have the number of the outputs of the trunk neural network to be equal to the number of the terms in the KL expansion. Okay. Okay. So now KLDNN model, it uses, linear representations of stochastic processes. We train them separately, so we lose some representability, but at least for this problem, we find that. So now why I think the error here is relatively small, smaller than in FNO and DeepNet. And of course, these models are more representative. They have more trainable parameters. Well, probably it's because the training data set is relatively small. So if we have more samples, we would expect, of course, that the errors in all three models will go down with more samples. But it could be that if we have, very many samples, that these two models would eventually become more accurate. But in real life, we don't have a lot of samples. Okay, so this model is not bad relative to, yes.
Very practical question. So how many simulations did you have for this particular?
Right. So in this example, I think we had 2,000 simulations. And this is a 700 dimensional problem in the sense that there are 750 nodes in the numerical model. Mm-hmm. But I think with KL expansions, we were able to reduce dimensionality to 100. So there was 100 terms in the KL expansion of the parameter.
And you were using the full field of the hydraulic head for training?
Yes.
And anything else, or?
That's it. Yes.
Is it steady state or transient?
Actually, this was a steady state. But we also did it for time-dependent problems. But actually, we found that for time-dependent problems, the DeepNet becomes very expensive. We were not able to train it for a time-dependent problem. So we actually have comparison of FNO and KLDNN for time-dependent problems, and they perform similarly. But the training time of FNO grows faster than the training time of KLDNN model. Okay, so now we want to use KLDNN to a model to analyze transfer learning in the KLDNN model. Okay, so now what is transfer learning? So according to Wikipedia, it's a technique in machine learning in which knowledge learned from a task is reused in order to boost performance on a related task. Okay, so now with application to this type of models, what we want to reuse the parameters in the operator learning model. So we want to reuse some of the values of theta for new conditions. Okay. So now so there are many different transfer learning methods, but most of them are based on purely empirical observations. And so what people found that convolutional layers and top layers in fully connected networks are general to the problem and can be transferred. So low fully connected layers are task specific and must be retrained. Okay, so and this is an example of transfer learning for the DeepNet. So they train DeepNet on a very large data set for one set of conditions, which is called source conditions. And then once conditions change to target conditions, what they did according to these observations, they transferred parameters in all convolutional layers. So they transferred parameters in the top layer of this trunk net. So these red connections show the parameters that were retrained. Right. And now they decided to retrain all parameters in this fully connected network that is part of the branch neural network. So again, you know, the choice what to transfer and what to retrain is very empirical. And I assume that they have done in this paper, you know, kind of fitting to figure out how many parameters and how many layers must be retrained. So in what we want to do, we want to understand what and when and why can be transferred and what must be retrained. So this is kind of the motivation for our analysis of transfer learning. Okay. So now to define it more specifically, this transfer learning problem. So what we do, we assume that our operator learning model is trained for the distribution of control variables with mean values, FS, GS, whatever. S stands for the source conditions. We assume that this model is trained using a sufficiently large data set. And then the TL task would be to construct a model for the target conditions corresponding to different values, mean values of the control variables. And we want to do it using a significantly smaller data set. Okay? So we train the model for one distribution of the control variables. Then we assume that the mean value of the control variables significantly changes, so the distribution shifts. We assume that the source and target conditions are significantly different. So there is very little overlap between the distributions of the control variables. So the question is what we can transfer from this model to this model and what we must retrieve. Okay. So what we do, how we do our analysis, we use the so-called moment equation analysis for stochastic differential equations. And the idea of the moment equation analysis is to start with the stochastic partial differential equations and then derive deterministic equations for the leading moments, for the mean, covariance, etc. So how we do this? We use Reynolds decomposition to decompose all our stochastic processes as they mean plus fluctuations. And these fluctuations, of course, have zero mean. Right? And then what we can do, we can then replace all these stochastic processes in our stochastic equation with these Reynolds decompositions, do some averaging, and then again we can derive the deterministic equations for the mean and covariance, and in our analysis we don't need higher moments. Okay? So now, once we have these equations, we can analyze them for the dependence of different components of the mean and covariance on target and source conditions. Okay? Okay, so let's start with linear partial differential equations. It's easy. So if we do this moment analysis, we can get an equation for the mean in the closed form, right? So this equation is exact. And if we look at this equation, we see that the mean under target conditions depend on the target conditions, right? So the mean depends on the target conditions. Therefore, the mean cannot be transferred. Right, in our KLDNN model, one of the parameters is the mean, so mean cannot be transferred. However, it can be easily computed from a deterministic PDE, and this is exactly the same model that is used to generate the training data set. So essentially, to compute this mean, we just have to get one sample under target conditions, but again, this sample should be drawn or obtained as the solution of the mean field equation, where the control variables y, f, h0, and g are replaced with the mean values. Okay? So we are going to call this mean field equation. So again, h mean cannot be transferred, but we need one sample to compute h mean for target conditions. So now, if we write equation for the covariance of H, it's going to have this form. Again, what's important here, that covariance doesn't depend on target conditions. Okay, so there is nothing in this equation with subscript T. Okay, so covariance doesn't depend on the target conditions, therefore, we can transfer the covariance from what we computed for source conditions to transfer conditions. We can, so covariance doesn't change, therefore eigenvalues and eigenfunctions don't change, so eigenvalues and eigenfunctions can be fully transferred without introducing any errors. Okay, so next we can write equation for fluctuations. And so what we find that for linear equations, the equation for fluctuations, again, it has the same form as equation for the mean. So it is linear. And then what we can show that number one, that the map from eta to psi is linear. So now theta here is the weight matrix. And this matrix theta can be fully transferred. Again, why? Because the equation for H prime does not depend on target conditions. Okay. So in conclusions, so now these two things, eigen functions and our parameters in the map can be fully transferred. We need just one sample under target conditions to compute H mean. So this amounts to what people call one-shot learning. And so we can prove, so this proves that one-shot learning is exact if and only if this one shot or the additional sample is drawn from the mean field equation. So for linear problem, you can make one-shot learning exact, but the sample should be obtained from the mean field equation.
Sorry, just to clarify, I might have missed, but X and X dash is the different domain, just so you need the cross covariance. X dash, X T dash is the different type. So you transfer from X to X dash. Sorry, I might be.
Well, covariance is a function, of two locations in space, but they're all from the same domain. So covariance tells us about the correlation between any 2 points in the domain.
Sure, thank you.
No, both these points are from the same domain. So 2 points in space, 2 points in time.
I have a quick question.
Yes.
I guess I don't really understand what problem you're trying to solve, which is like in the earlier section, you had some sort of KL expansion. Let's say for the input, some function of space and time. You have it you expand in terms of the mean and then your basis functions, which you learn from data, right? So once you have that, you regress for the coefficients of the KL expansion, send that into your neural network, and then you get something out. If I give you a new data point, let's say in your digital twin example, I just give you another control, which is the function of space and time. You could still do this projection to get the coefficients. Like you're not really leveraging the statistics of your KL expansion all, right? It's just you have a basis, you expand it, and then you learn the new coefficients.
Right. But however, if this value is of the control variable for which you want to evaluate the digital twin, if this value is out of the distribution of the control variables for which we train the digital twin, then you don't expect your prediction to be accurate.
Okay, like, so it's really like the distribution of the coefficients of the KL expansion, you think you might have something in the tail where you don't have enough data, and so it's just your network's not going to be accurate.
Well, in fact, what we do is much simpler. We assume that the distribution of the coefficients doesn't change. What changes is the mean value. Okay. Because in the KL expansion, it's the mean plus the sum of the coefficients. So our question is what's going to happen if the mean significantly changes. If, for example, the sample of the control variable, comes from a distribution with a very different mean. Right? So, for example, well, there is no mark, but that's okay.
But in principle, that mean shift you would detect by projecting onto each of your basis functions, right? Like you could in principle absorb it, and you're just saying that.
No, we can definitely do it.
Right.
But then what we will probably find that this size will be shifted. They will not have zero mean. Sure. Right. So how to account for it?
Okay. Thanks.
I don't know what happened. So now, so it's 12:52. Okay, so I will have to, skip the third part, but I will just finish with transfer learning for nonlinear PDEs. Right, so now the analysis for nonlinear PDEs really depends on the form of the nonlinear PDE. So we want to consider a simple one. So now we want to treat K as a control variable. So now why this equation is nonlinear? Well, because in general, K is unknown, H is unknown, so there is a product of K and H, which makes this equation nonlinear as far as our analysis is concerned. Okay. Then this equation is subject to some initial and boundary conditions. So now again, we assume that K is the control variable. We represent it again with the KL expansion. This is our KL-DNN model that predicts H as a function of psi coefficients in the KL expansion of K. And so now we assume that what changes from source to target conditions are the initial and boundary conditions. Okay, so we trained the model for one set of initial and boundary conditions, and then we want to retrain it for very different initial and boundary conditions. Okay. So now if we do a similar moment analysis, we will come up with this form of the mean field equation. So now you will see, you will find that because this equation, the starting equation was nonlinear, our mean field equation has this non-local term. Yes, it's a product of fluctuations in K and H. So now we cannot solve this equation easily to compute. So now this equation, we want to solve for target initial and boundary conditions. However, in general, we cannot solve it easily, definitely not with one sample because of this non-local term. So however, if our K field has a relatively small variance, or more specifically, if the standard deviation divided by K mean is less than 1, then we can show that this term is much smaller than these two terms, and we can ignore it. Okay, so again, for small variances, we can transfer mean by solving this approximate mean field equation. So now for the covariance, the equation is complicated. I'm not presenting it. However, again, from the moment equation analysis, what we can show that the changes in the covariance of H are on the order of, or changes in covariance of H due to changes in the boundary conditions are on the order of epsilon divided by L, where epsilon is the change in the boundary conditions and L is the domain size. Okay? So now for most natural systems, for example, aquifers, changes in the boundary conditions are on the order of, I don't know, meters. The size, so epsilon is on the order of meter, L is on the order of hundreds or thousands of kilometers. So this ratio is very small, so we can ignore the changes in the covariance. So the covariance can be transferred, meaning that eigenvalues and eigenfunctions can be transferred. Yes.
Does that apply to changes in K as well? Because
No. We assume that the distribution of K does not change.
Okay.
The only things that change are the initial and boundary conditions. Yeah.
I have a related question,
Yeah.
Alex. So the magnitude of epsilon, intuitively it seems to me that it will depend on the structure of K.
Well, again, the epsilon is the change in the boundary conditions.
Okay, so you said,
So essentially, the problem is like this. We train the model for one set of boundary conditions, then the boundary conditions change. We need to retrain our model.
right. So my question was not properly posed. So you say that the changes in the covariance are of the order of epsilon over L.
Yes.
The constant in front.
Oh, I see. Yes.
Intuitively seems.
Right.
like
No,
it
you are
could-
right. You're absolutely right. But again, here we're still in this regime where variance is small.
Okay.
Yes, you are right. For large variance of K, the coefficient in front would be larger, but we are operating under this small, yes. So this guy can be transferred. So now if we look at the equation for fluctuations, it is nonlinear, number one. Number two, it depends on the target conditions. So what it means that the map from eta, from Xi to eta is nonlinear, number one, and number two. In general, parameters cannot be transferred. So, and for this, we just use standard approach from transfer learning. So in this neural network, we transfer parameters in the top layers, in all layers but the last layer, and then we retrain the parameters in the last layer. So now the neural network, if you know, is linear with respect to the parameters in the last layer. Well, usually we pick linear activation functions for the last layer. So now retraining this neural network becomes a simple least square problem, which is relatively easy to solve. And so these are our results. So they are for this ratio of sigma k to k. So this ratio is less than 1, equal to, well, in fact, it's not less, it's equal to 0.6. And then, so this is the comparison of the exact solution and solution given by our model at different times. So we have, good agreement. So these are boundary conditions. The initial condition was that head everywhere is equal to this value, right? And so now these are our target conditions. So you can see under target conditions, the boundary conditions are completely flipped. And so now we can get this solution. So we can retrain our neural network with only 5 samples. And so this is the error in the model for the source data set that is trained with 1,000 samples on the order of 10 to the minus 3. So this is the error in the retrained model. So it's slightly larger, but still of the same order. And in this case, the dimensionality of the problem is 20. So we use 20 KL terms to represent K. Okay, so now this is an example of a few shot learning. So we need a relatively few shots to retrain the model. Again, what we proved that, or we demonstrated that some parts can be transferred, but again, we have the conditions when they can be transferred. If these conditions are not satisfied, then I guess nothing cannot be fully transferred. And then this model must be retrained. Okay, so I think this is all that I have time to present. So I will skip through my Bayesian stuff and just, well, I think this is the slide where I want to stop. So what I described, what I presented can be found in this paper. And this is the paper that describes, well, the other way around. So this paper describes the transfer learning, and the first paper describes the Bayesian methods that I didn't have time to present. Thank you.
We still have time for a few questions. It's one or two.
Thanks for the great talk. Very interesting. Setting aside the neural network machine learning stuff, you do a really interesting, procedure where you create the KL using sample statistics, the ensemble mean, the covariance operator. My first course in statistics is going to tell me, right, that Monte Carlo error is on the order of square root of n, and you have an order of 1,000 simulations. So your ensemble mean, I would expect, is going to be biased by like square root n, 10 to the minus 1.5. You're getting L2 error that's 10 to the minus 3, 10 to the minus 4. Where are you getting that extra accuracy?
Well, there is always a coefficient in front of 1 over square root of.
Yeah, but
Yeah,
it could be bigger than 1, smaller than 1.
Right.
Much smaller than 1 is kind of unexpected to me. So I'm kind of asking where do you get this intuition for it?
Well, so the accuracy of the digital twin will always depend on the number of samples, right? So, it's a regression model at the end. Yes, and, in this case, at least, as you noticed, we have an estimate for the error, right? In other models, we don't have this estimate. For example, if you, compare it to other operator learning models like FNO, DeepNet, you are absolutely right. The error will depend on the number of samples.
Thank you.
Right, so there is, you know, well, again, why is this my specific order of the error? Why it is smaller than 10 to the minus 3? It's a good question. I don't know. I don't know. It's a good question.
Ask one
Yeah.
question. So I think that KL expansion basically sort of adds some structure in a sense that you can have less less computation because you kind of add the structure like mean plus covariance. So if it's, for example, it's not super Gaussian, this approach doesn't work. Have you tried sort of like how far you can deviate, or this like a neural network kind of can address sort of the non-Gaussian part?
So it's a good question, and Yusuf is an expert, can correct me if I'm wrong, but you know, KL expansions can be used to represent any process.
I see.
It can be used for representing non-Gaussian distributions, such as these random variables will be non-Gaussian. But if you notice that our analysis doesn't care about the distribution, at no point we are using the properties of the distributions of the random variables, because at the end we are not actually mapping the distributions.
Sure, but you use this mean
Right.
as sort of the representative, but the mean has to be somewhat representative
It's
of
a sample.
the
It's
system.
a sample mean or ensemble
Sure.
mean.
I
Yes.
see. Thank you.
Here you're doing a KL expansion for the control and the field separately.
Yes. Yes.
I ever consider like doing a kind of funding, but like by doing so, your leading mode in the control is not necessarily an optimal mode that give you the optimal response in your function. Have you ever considered like doing a decomposition by finding the control data and the response data together and kind of find optimal, linear optimal forcing mode and linear optimal response mode, and then doing your learning on those coefficients?
So this is an excellent point. So we haven't tried this, but we tried a single KL expansion for all control variables, because quite often control variables are correlated. So you are right. It's a good, you know, good thing to test. Yes.
Okay, yeah, again, thank you very much for a great talk, and yeah, thank you so much for coming.